You have probably stared at a tiled floor while waiting somewhere square tiles, 4 to a corner, or hexagons, 3 to a corner, the honeycomb you see on bathroom walls. They lie down flat and cover the whole floor with no gaps and no overlaps. So try this in your head. Swap the hexagons for octagons, 8 sides each, and keep 3 of them meeting at every corner. Lay one down, and it is fine. Add its neighbors, and you run into trouble. 8-sided tiles are wide, and 3 of them crowd a corner with more material than a flat surface can hold. The floor cannot stay flat. To fit them all in, it has to pucker. And every single corner buckles into a little saddle. Do that everywhere, and the whole floor curls away from you into a shape mathematicians call hyperbolic. It is the opposite of a ball. A ball wraps around and closes up. This thing opens out faster and faster. So there is always more edge than you would ever expect. A floor that refuses to lie flat is already strange enough. Before we explore it, sit with 2 plain questions. First, cool almost anything down far enough and it locks into a fixed pattern. What would it take for a material to keep shifting forever, never freezing even at absolute 0? Second, if you bent a material's whole world into that saddle shape, what could happen there that no flat sheet could ever allow? Now, physicists have a magnet they can solve exactly on paper, on the flat honeycomb. It is called Kitaev's model. And we will get to know it. The tempting thing to say is this: put that same magnet on the buckled octagon floor instead, and you will just get a crumpled up version of the same physics. A messier picture that tells the very same story. So before we go one step further, sit with that guess. Bend the solvable magnet onto the saddle. Does it get harder to solve, or somehow easier? And does anything genuinely new show up that the flat floor could never give you? Let's start with what usually happens, because this whole story is a break from it. Picture a material as a grid of tiny compass needles. Physicists call them spins. When it is warm, they point every which way, knocked around by the heat. Cool the material down, though, and they stop fighting the heat and start listening to each other below some temperature. They snap into a pattern and hold it, all pointing one way in a fridge magnet or neatly alternating in most others. The material freezes into magnetic order, and almost everything obeys that rule. But you can rig the game so the needles can't all agree. Put 3 of them on a triangle and ask each pair to point opposite ways. 2 of them manage it. The third one's stuck. Whichever way it turns, it lets one neighbor down. That deadlock is called frustration, and it is the crack we're going to pry open. Now turn up the quantum mechanics on a frustrated lattice, and something strange becomes possible. What if the spins never picked a winner at all? Instead of settling on one compromise pattern, they keep exploring all of them at once, resonating between arrangements, right down to absolute 0. They never freeze. There is no final pattern to point at. A material like that has a name, a quantum spin liquid. And it is exactly the never-freezing material the first question asked about. In a moment, we'll meet the one example we can actually solve with pen and paper. The trouble is, never freezes is easy to say and painfully hard to prove. For almost every model like this, you can't solve the equations. You are stuck guessing with approximations that might be lying to you. Which is why one particular model written down by Alexei Kitaev changed the game. It is a frustrated quantum magnet you can solve completely, exactly, by hand. And when you do, you learn that a disturbance in it doesn't travel as a tidy ripple. It comes apart into brand new pieces, and those pieces are what we look at next. So what makes Kitaev's magnet special is the shape of the disagreement. On the honeycomb, every spin has exactly 3 bonds, and he painted them 3 colors. On a blue bond, the 2 spins only argue about their up-down axis. On a cyan bond, only their left-right axis. On a magenta bond, only the third one. Each spin is being pulled to line up 3 different ways at once, and it can only ever satisfy one of them. The frustration is built straight into the colors. Before we take this apart, get these few pieces into your head, because we follow every one to the end, a spin and the strength it is pulled with. The piece we're about to split it into, a little central one we follow everywhere. Its three partners, one guarding each colored bond, the single number those partners lock into, and saved for the end, one extra twist we switch on later. Kitaev's trick is to stop treating each spin as one solid object. He splits it into four simpler pieces called Majorana fermions. Think of them as bare, stripped-down half-particles. Each spin becomes one central piece, which we will call C plus three outer pieces, one assigned to each colored bond. On screen, that is the whole trick in one line. The spin equals the central piece times a bond guard. Now watch what the outer pieces do. On every bond, the two guards that meet there lock together into a single number that is either +1 or -1, nothing in between. We call that number U. And once they are locked, they stop moving. They just sit there, a fixed pattern of plus and minus ones laid across the whole lattice, like a frozen maze. And that leaves the central pieces, the C's, completely free. With the maze frozen in place, each C simply hops from site to site through it, like one particle wandering a fixed set of corridors. A hopelessly tangled magnet of interacting spins has quietly become one free particle moving through a static background. That is exactly why you can solve it. Quick commit, because I promised you this right at the start. Poke this frozen magnet. What actually moves? There it is. Poke this magnet and you do not get a neat wave of tilting spins. You get these fractional pieces walking off on their own. The spins came apart. So the first question on our board is answered. This is a real material that never freezes. Its disturbances fractionalized, and we can prove every word of it. Here is one to predict before we bend the lattice. You get to choose which one of your three colored bonds to satisfy. Can a single spin ever satisfy all three of its bonds at the same time? So let us actually move Kitaev's magnet onto the buckled floor. We cannot draw a hyperbolic tiling flat without cheating. So we use the standard cheat called the Poincare disk. Picture the entire infinite saddle squashed into one circle. Everything looks shrunk near the rim, but every octagon out there is really the same size. The crowding is just the toll you pay for flattening a curved world onto a screen. And just as we wanted, three octagons meet at every corner. Now here is the one deep way. The saddle is far more than a messy honeycomb. On the flat lattice, moving is simple, step east then north, or north then east. And you land in the same place on the saddle that quietly stops being true. Take two steps in different directions, and the order matters. You end up somewhere different depending on which you did first. The lattice's own symmetry has gotten tangled in a way flat space never is. Keep that tangle nearby. It comes back first to bite us, and then to save us. And this is why that tempting guess, just a messier honeycomb, should have you worried. Because to even define Kitaev's model, on this thing you need two hard things. First, the coloring. You have to paint every bond one of three colors, so that no two of the same color ever meet at a corner. On a tidy repeating lattice, that is easy. On a general graph, it is one of those problems that can take longer than the age of the universe to solve. Second and worse, that frozen background of plus and minus ones. The physics only fixes it up to loops. Go around any one tile, multiply the U's along the way, and you get a number physicists call the flux. The true ground state of the magnet is whichever pattern of fluxes costs the least energy. On a big lattice, there are 2 to the power of the number of tiles patterns to check. That is not a calculation. That is a lottery with astronomically many tickets. So on paper, bending Kitaev onto the saddle looks like trading a solvable model for a hopeless one. 2 impossible-looking problems stacked on top of each other. If your gut says the curvature just wrecked everything, that is exactly the trap I want you standing in. One more commit before we spring it. We are about to reuse the very same trick, splitting each spin into Majorana pieces on the curved lattice. Does that trick survive the bending? So now the payoff for all that worry, because the curvature does not wreck the problem. It hands us the answer. And the reason is the very thing that made the lattice weird in the first place. It's symmetry. Look at the saddle tiling again. Because it is so regular, you can slice it with a mirror line. A perfect reflection that leaves the entire pattern unchanged. On the flat honeycomb, there are only a handful of those. On the hyperbolic lattice, there are infinitely many, running in every direction, cutting straight through every tile. And there is a classic result called Lieb's lemma that says something clean. Whenever a model like this has a mirror symmetry, its frozen background has to respect that mirror too. The plus and minus ones on one side must reflect into the ones on the other. One mirror pins down a handful of them. But with mirrors running everywhere, you can corner every tile in turn and force its flux. That astronomically large lottery collapses into a short, exact calculation. Now, a fair worry, in the student's words, infinitely many mirrors sounds like more demands than the poor lattice could ever satisfy. Doesn't it just tie itself in a contradiction? It is a good worry, and the answer is no. The mirrors do not fight each other. Each one only relates a tile to its own reflection. And because they all descend from the same underlying symmetry, their answers stitch together perfectly. More mirrors simply means more of the pattern is decided for you for free. So let's predict the answer together before it drops on our 8-sided tiles. What does that forced flux actually come out to? Lock in the one you believe before you read on. And there it is. Every octagon carries the maximum flux, what physicists call π-flux, exactly the same on all of them. It comes from a formula so simple it is almost cheeky. Count the sides of the tile, have that number. And whether it is even or odd decides everything. The 6-sided honeycomb gives you 3, an odd number. And the flux comes out to 0, which is Kitaev's original answer. Our 8-sided tile gives you 4 even, and the flux flips to the maximum instead. The shape of the tile alone picks the ground state and the coloring we were so afraid of. On an even-sided lattice, the sites split cleanly into 2 families. And that is exactly what forces the clean 3-coloring Kitaev's trick runs on. So the guess we started with was backwards. Bending Kitaev onto the saddle did not make it harder to solve. Its own curvature made it easier. One commit before we cash this out. We have just frozen the whole background pattern solid, pinned by symmetry. So has the magnet itself finally frozen too? All right, let us actually turn the crank once, because it is short and worth seeing. Start with 2 spins on a single bond pulling on each other. Swap each spin for its pieces, the central C and the bond guard. Multiply the 2 together. The 2 guards on that bond fuse into their frozen number U, and the 2 central pieces sit side by side as a simple hop. The messy spin-spin term becomes J times U times a C hopping to its neighbor. One clean line, and every bond in the whole lattice does exactly the same thing. Try it yourself on a piece you haven't seen. Take this fresh bond written in spins, and using the same swap, work out which hopping term it turns into. Lock in your answer, then watch it happen. The 3-spin term, the twist we held back, does the same collapse, except it links a C to its next nearest neighbor, hopping across a tile instead of along a bond. Stack every term together, and the entire magnet is now just this, one matrix that tells free particles how to hop through the frozen flux. A magnet of hopelessly tangled spins rewritten as a single hopping problem. That is the exact solution in one picture. One quick test of that flux rule on a lattice we have not solved. Everything we are about to see rides on the forced background flux. If the tiles were 6-sided instead of 8, what background would it be? Now, a free hopping problem on a flat crystal is a solved art. You go to momentum space, use Bloch's theorem, and you are done. But remember that tangle from before, where steps in different directions do not commute. Ordinary momentum space quietly assumes that they do. So here the standard method does not just get harder, it gives the wrong answer. The fix is to allow richer labels. Instead of one phase per direction, you need whole blocks of numbers that themselves do not commute matched to the lattice. Physicists call these non-abelian block states. You cannot write them all down. So you do the practical thing an engineer would do. You wrap the lattice into bigger and bigger repeating cells. A ladder of them up to a couple of thousand sites, and you watch the answer settle. Then you check it against a completely different method run on chunks of 100 million sites. And the two agree to the eye. Out of all of that comes one plane graph you can read at a glance. It counts how many low-energy ways the C particles have to move. And physicists call it the density of states. It is the single dial that tells you which strange phase you are in. So here is what I want you to sit with. On the flat honeycomb, right at the perfectly balanced point. That graph pinches down to 0. There are almost no low energy moves. It is a razor-thin situation. Predict what the saddle does to that pinch. Does the curve keep the razor-thin 0, or does it fill it in? So here is what the saddle does to that razor-thin pinch. It fills it in on the hyperbolic lattice, right at the balanced point. There are plenty of low-energy moves. The graph sits at a healthy finite value where the flat honeycomb had almost nothing. That sounds like a small technical difference. It is not. It means the curved magnet lets its fractional pieces flow freely at 0 energy, like a metal made purely of Majoranas. And no flat lattice can do this. The honeycomb's razor pinch is forced on it by flat space. So the second question on our board is answered too. Bend the world into a saddle, and you get a metal that flat space simply forbids. And this traces straight back to that tangle from before. If you had used the naive flat space method, you would have wrongly predicted the pinch survives. The filling in is the fingerprint of those richer non-commuting states. The ones only curved space forces you to use. Ordinary flat physics cannot even see them. Now slide off the balanced point and make one color of bond much stronger than the other two. The metal gaps out, and you land in a different phase, a gapped one. In this corner, you can solve it a second, cleaner way, and it turns into something famous, the toric code, the textbook material that hides information in its knots. Its disturbances are anyons. Particles that are neither quite bosons nor quite fermions drag one all the way around another, and the whole system quietly remembers with a minus sign. This is the tame, well-behaved kind of enyon. And every bit of it sits on top of that forced π-flux background we pinned down earlier. Quick, no looking back, what flux does an 8-sided tile carry, and why that instead of 0? Good, now for the last phase, switch on that twist we held back, the 3-spin term k. It does one very specific thing. It breaks the symmetry between running time forwards and backwards. And the instant it does, a gap opens at the balance point and a brand new phase wraps around it. This one carries a whole number called the churn number, equal to -1. And an odd number like that is the calling card of the wild kind of enyon, the non-abelian kind. The sort people dream of building fault-tolerant quantum computers out of. And whenever the inside carries that number, the edge is forced to carry a current that flows only one way, a chiral edge mode. On a disk of these octagons, you can actually watch it, a single ribbon of state skating around the rim, its energy climbing in a straight line with how fast it circulates. The telltale sign is that the allowed values are half integers. Never landing on zero, poke a vortex through the middle, and that whole ladder shifts by exactly a half, pinning a lone Majorana right at the center. Curvature even changes how many edge states there are. Because the saddle is almost all edge, you get a whole extensive army of them, not the thin skin a flat flake would give. So look back at the guess we started with: bend Kitaev's magnet onto the saddle, harder to solve. No, the mirrors made it exact, just a crumpled honeycomb, not even close. You get a medal of Majoranas, a tame liquid, and a wild one, 3 states of matter the flat model never had. Before I give you the summary, let us see if it's stuck. I will name a piece, you fill it in. First, what did we do to each single spin to make the whole tangled thing solvable? Second, what pinned down the frozen background, the flux, without ever checking a trillion patterns? And third, what never happens to this magnet, no matter how cold it gets? So, plainly, take a magnet you can solve by splitting each spin into fractions. Bend its whole world into a saddle. The curvature's own mirrors hand you the answer, and out fall 3 states of matter that a flat sheet could never hold. And if you keep just one thing, keep the word, the whole solution turns on: flux. The F is for fractionalize. You split every spin into pieces. The L is for Lieb's mirrors, which pin the flux. The U is those frozen U's, the field the pieces move through. And the X is for the exotic phases that fall out, the tame liquid, the wild one, and the metal that flat space forbids. Both questions on our board answered. And one last thing to leave you with, which I am not going to answer. We did all of this on the 8-sided tiling, but there is a whole infinite family out there, 10 sides, 12, and on, each one bending space a little differently. If the octagon hands you a medal of Majoranas, what do you suppose is waiting on the others?